So, 你在公信界怎么过？ So, we have passed from last time. So let's review a little bit because I mean, last time I made a lot of mistakes. There was some flow of core explanation. So let's review, recap a little bit to warm up your brain. To warm up your brain, and then so permanent low temperature, we did thermofield expansion, and using thermofield expansion, we derive all the thermodynamic quantity from statistical mechanics ensemble. From your statistics. And we derive this one, and then so from here, I have hard time to derive this one 5 over 10. So here, 5 over 3, and then 1 plus this term. I hope, so I just, sorry, 50, this is 15. Effective Fermi energy, and 5 over 2. But here, you need to keep track of all the limit term, which is proportional to t to the square. Which means that the inertia to this term, you have to plug this one to here and expand it and 5 over 2. So you have this one. Essentially, what's going to happen is that the 5 over 2 is it. Everything 5 over 2, and this is 5 over 2. This means that the what you get is that the epsilon f here 5 over 2, and then consider this is small quantity, and this is 1 minus 5 over 24 I squared, and then this. So this is the equal, and then this like this. So I just do that the tail expansion of this one, and the 5 over 2 times 1 over 12 is 5 over 24. And the 5 over 8 minus 5 over 24 is in fact 5 over 12. And then pi squared, and then this plus why, I mean, the note was okay, so but I couldn't derive last time. So, simple calculation, but I get that. So, if you make a, if I couldn't derive, please, actually, one of the students for what I missed here last time. So, if you miss something, please let me know. I often make a mistake. Another thing is that the both thermofield expansion, both Einstein condensation, there's a critical temperature T, and if you slightly above critical temperature, how does it behave? And then we did the following thing. So 1 is equal to pi squared over 4 to infinity. And then e to the epsilon theta minus mu theta and t theta minus 1 of theta, and then apply over 4. And then here you separate the contribution on half e to the epsilon theta over t theta minus 1 plus pi over 4. So since the t theta t is less than or equal to critical temperature, then theta is equal to V. So chemical potential is over Z. So recall that so we derived last time that the so this is mu and temperature T, and then for thermofield the critical temperature heats enough, and it was zero. The chemical potential for the boson at the low temperature is zero. And then from there, so what you have is quadratically decreasing. So what we derive from here is in fact, here is some constant, which is not important. That's what we derive. Okay. So therefore, so we treat mu as very small. And then what we did is that we separate contributions from E to the equivalent and equivalent and 1 minus E equivalent and 1 and times the equivalent of E. That's what we did. And here, what we did is that we just took the leading contribution. So here, we approximate to the equivalent is from here minus equivalent minus equivalent is from here by just taking the lower expansion of E and 1 plus equivalent blah blah blah, and then we just pick the leading order, and then we substitute this. We just use this approximation and to derive this. But this is only valid since mu theta is very small, and we only look at the leading fraction to the mu leading subcorrection to the mu theta. That's why this is allowed. But if you try to include, so from here, so if you do the whole integral by using this approximation, what you get is that in fact some constant minus the pi square over 4 is here not you here one half. That's what you did. That's what you get. But if you try to get the order of mu theta, the subleading fraction of the mu theta, this approximation is not valid. It has to be a bit more good. But this approximation is valid only the leading fraction. That's what I'm not sure. Then we move on to the, so this is the ideal gas. So I think the ideal gas in Chinese tradition, the second Japanese. Ideal gas there's no interaction, and we try to move on to the interacting system. But before that, to move on to the interacting system, so ideal gas is the particle is freely moving by thermal fluctuation, and there's no interaction between them. There's no interaction. That's a situation idea. But later, so maybe 2 or 3 lectures later, so we will learn Landau's Fermi-Liquid theory. So that there, so you have to really increase for the interaction. But even if you include interaction in terms of the Fermi-Liquid at a low temperature, it almost became like a that's what the ingenious of Landau tells me. But that's what we're going to learn. But before going that, we will just first learn the density metrics. Density of rho hat is essentially nu phi, whatever psi or whatever you call it. What's my notation? Psi I nu, psi nu, and the probability. That's the density metrics definition. So this is the problem statement. probability of state. And then this is the destination system. And then if you try to compute the expectation value of this such a statistical system, you have to include trace from path and all possible hero space. All possible hero space. You have to trace over all possible. That's what we do. In particular, the canonical ensemble row count is the fact one with B sum over state psi nu and the E3 minus like this. So more precisely, if you write using operator formulas, and this is E to the minus H hat KT. That's what you. And some students ask you, what's this? Can you treat this like a matrix and so on, or operator, whatever you call it? So if you don't understand the exponential of some Hamiltonian, you just do that Taylor expansion 1 minus H hat. Okay, I don't like a KBT, so that's beta H hat plus 1/2 beta H hat squared plus whatever. 3 factorial beta H hat the Q and so on. So you can take the Taylor expansion, each Hamiltonian can be treated as operator, right? And so therefore this can be treated as operator. Okay. And in particular, so if psi nu is the eigenstate of Hamiltonian for each hat can be understood as a nu and then nu like this. And since the psi nu and psi mu are some eigenstates of Hamiltonian, this should be replaced by epsilon nu delta u. Okay? Like this way. So therefore, if you plug this one into here, so what you get is this dot upstairs. So that's how you compute as a density matrix as a matrix or operator, whatever you call it. Okay. So that's the case. Fine. And then yeah, and then identical particle independent because an infinite particle is from energy, and if you have the state, whatever, you have a state like this state, whatever, this is psi 1, psi 2, psi 3, and so on. This is ground state psi 0, and so on. If you do bosons, you can have multiple number of particles. And so on. So this is so therefore n0 equals to 3, and then 1 is equal to 1, and 2 equals to 2, and 3 equals to 1, and 4 is equal to 0, and so on. So those are the states of the bosonic system. And 0 and 1 is the fault space you can have. Then this is 3, 1, 3, 1, 0, 2, 3, 0, and so on. Okay. Those are bosonic states. On the other hand, for fermionic state, you can only have one of these. Whatever, like this. So in fermatic state, you have 1, 0, 1, 0, 0, 1, 0, 1, and so on. You can have this is the fermatic system. Okay, and then, so if you consider graphical ensemble, you can have the partition function is a partition function trace of so trace of row has to equal to 1. And the granular ensemble, this is 1 over Z, is trace of E3 minus H hat minus mu n hat. Okay, so that's times value. Times value. That's what we have. Therefore, partition function is trace of E3 minus value. And hat. Okay. And in the case of this empirical, so this can be replaced by E3 minus beta epsilon nu minus nu and half nu. And sum over all possible product over all possible nu. Product over all possible nu. So n hat is the numbering operator that counts the number of particles in each state. Okay. So therefore, and this can be understood as the product of nu trace of E3 minus beta like this thing. And we treat this entire thing as this definition as the each state partition function. So you can easily see nu can be understood 1 plus E to the minus beta is from nu minus mu for fermions. For the bosons, you can have multiple things. Like this. Those are the logic system and upward fermionic system. So trace all possible statements here. For fermion, you have a 0 or 1. 0 corresponds to 1 and then 1. Or 0, 1, 2, 3, 4, and so on and so on. So you have okay. And then so the quotation value of n hat of nu is the trace of rho hat and hat nu. Let's derive this from the for fermion. For fermion, so you have rho is the same as before. And essentially, so you have n hat is 0 or 1, right? For fermion. If it is n hat, so if you just have so this means that 0 rho hat and hat 0 or 1. Rho hat and hat 1. That's the particle output. Okay. So what's this? So this should be 0 because NC 0 to be 0 because it's an N to be 0 because 0. 0 times whatever is 0. This is 0, you ignore. So this is what? N is equal to 1, right? Rho is just over there. So this is E to the minus beta over product is shown here, here, but divided by this is one over z. One over z. One over z is this guy. So this guy is 1 plus e to the minus beta, it's mu minus mu. And this is equal to e to the beta, it's mu minus mu, plus 1 divided by 4 carbon. So this is parameter of statistical distribution. On the bottom case. So this is the bottom. So let's go to the bottom case. So here you have the same thing, 0, rho hat, and hat, new, 0, and next is 1, the same thing. And next is 2, next is 3, and so on. Okay. And what you get is what? What you get is the 1 over z. 1 over z, and then here you have the e to the minus beta, it's from mu minus mu, plus 2 e to the minus 2, and that is from mu minus mu, plus 3 e to the minus 3, beta is from mu minus mu, plus like this. So now it happens because 2 and 3 are due to this numbering operator. What's this? So this is equal to, so if you plot out the computation, so okay, so what's this number? So x plus 2x plus 3x squared, let's start, x squared, x cubed, 4x to the fourth plus dot. What's this? This is e to the x, comma. You agree with that? Okay. So this is equal to x, comma x squared. Okay? X is e to the minus beta, blah, blah, blah. So this means that this is equal to 1 over z is what? Z is 1 over 1 minus z. So 1 over z is 3, 1 over z minus z minus beta is u minus 3. And here you have e to the minus beta, it's u minus 3, divided by 1 minus e to the minus beta, it's u minus 3. Sure. Okay. This is equal to 1 over e to the beta instead of minus mu minus 1. So this is a both Einstein distribution, both distribution. That's how you get from this density matrix formula. Fine. Okay. Any questions about that? Okay. I think more for example, we're going to move on to, and also you can have density matrix by position representation. So rho x prime beta is equal to beta e to minus beta h hat x and x prime. And this is equal to half of beta. And N and M. If N and M are also normal system, so here what you get is essentially what you get is delta N M e to the minus beta gives N. That you get. For example, this is equal to psi x n psi n x prime star and e to n. Thank you. That's what you get. you take a derivative with respect to beta, with derivative with respect to beta, it's super easy to see that the delta V is beta, and rho x prime beta is equal to times h at rho x prime beta. So this can be free. So this is called normalization. Normalization. Equation. Or it's just another algebraic equation. Where beta is treated as an imaginary part. So imagine. Okay. So that's the next symmetry. So and then so we can have the following like a say multiplicative property of the symmetric. Like this thing. So this is super easy because I mean this is in fact equal to x2 e to the minus beta. No, sorry. Tau 1 plus tau 2 h hat sp. But this is if you insert in the middle of the identity operator, you can have this x2 e to the minus tau 1 h hat tau 2 x1 e to the minus tau 1 h hat and xp. Okay, that's what you do. This is exactly this. So that's what you do. And in this coordinate representation, so this is a positional representation. This is for position. Representation or presentation, whatever you call it. So O hat is the so O and you can put the X and X and rho hat and X prime and then X prime and then coordinate dx dot. You can have. So we call them, and then you can always have the dx integral. Anyway, minus infinity. So this is identity matrix can be treated. So this is equal to. I call this x prime, rho x prime, x. Sorry, I think we'll do the opposite. But how we obtain the expectation parameter from opposite. We need to So now, so if the path integral formulation of this density, path integral meaning of the density matrix, that's what I was supposed to do from the lecture, but anyway, so it was nice to recap because I mean, it's already past 2 weeks. But 2 weeks passed already in the last lecture. So now we move on to path integral. And how many of you learned about the path integral already? Okay. It's the food education, okay? Who teaches economics? Who teaches economics? Nobody teaches economics. Okay. That's kind of okay. I worry about the food education thing. Last integral. Okay. Last integral. The part who is the father of the last integral? Okay. Well, I'm gonna think about Paul. So the image is there's a double slit experiment. So if there's a source of the whatever particle, and then in quantum mechanically, so you can have this path, and have this path, and this path can be allowed. And if you have a superposition of this wave, two paths, and then you can have whatever. You can always sum over all possible two wave function like this. Then what you have is whatever. What I call this double slit experiment. Anyway. So this kind of pattern we'll see will be at the wall. I'm asking, what if you add this one more hole? Sure. You need to consider another path. Quantum mechanically like this. You have to sum of three possible wave function, and then also here you have to another wave function to consider to describe pattern of the wall. Furthermore, I'm gonna ask what if you put another slit like this way? Okay. What if you have like this? Then now you can allow such a path, this one and this one and this one, or you can have this one, and this one, and this one, like this one. For example, there are totally 3 times 3 possible paths, 9 possible paths. And so on. What happens if you add one more slit and so on? And so just keep doing. So now for quantum mechanically, what you need to consider is all possible paths from the source to the target. Say, so if you consider this point, you need to consider all possible paths. Whatever path is the, if you consider infinite many slits and infinite many holes. Okay. You need to consider some of all possible wave functions in quantum mechanics. So that's what final will do. Okay. How do you mathematically formulate this into the how do you formulate this idea mathematically? Okay. Okay. Suppose we have stage 5. Is the in quantum mechanics it is unitary equation of psi. Okay. So psi of time t is related to psi of time 0 by unitary time evolution operator. Okay, and then here if you take the formula main function of t, what you get is that dx dot infinity like this. So we write it down this way is the like this here. Okay. So that's what is going to happen. However, here's the time version x naught from xx. Suppose this is x naught here, and this is xf, and then time t. Okay, so t equals to. Okay. So all possible time version from here to here is described by this one. So we can still subdivide this process, subdivide this process in the middle. In n times, capital N. Okay. And then what's going to happen? Okay, so let's call this is T final or Tn, whatever Tn is equal to e to the minus I h bar of h hat of t, which is the very stupid thing. T divided by n and multiplied by capital N. Okay, and I call it this one is equal to u epsilon. U epsilon, where epsilon is equal to t over capital N. Like this. So I just subdivide this process from here to here in the infinite many, anyway. It's the same as what you put is an n slit in the middle. N slit in the middle. Roughly. Okay. So then, so what's this operator, unitary operator from? So this can be understood as xn u epsilon x naught, like this. And this one is equal to I to the 1 to n, dx I, 1 to infinity, and then you have xn, u, this one, and the xn minus 1, xn minus 1, u, 1, xn minus 3, and so on, and then x1, u, like this way. Okay, that's what's happening. So here, instead of n, I call it capital N. Okay. So here, you just put the x1 integral means that so here you can have all possible positioning around here. What's possible? The next is the same thing. Integral over. Okay. So this one can be treated as I So this one can be treated as one, two, and one, and then my infinity dxi u not equal activity, and this will be equal to what's going to happen. And here the Hamiltonian for between the product on minus 1, I go to 1, xi, and then xi, e to minus I over h bar p squared plus b xi minus 1, like this. Times epsilon, times epsilon. This is Hamiltonian. So, okay. And then now also what we need to do is to insert the position operator. So dxi and dpi, and then what we have is xi, the e to minus h over 1, p squared, p epsilon, and pi, xi, and then so here b only depends on coordinate x, not p, momentum. Therefore, you just have like this xi and this. So now it's no longer operator. This is just some p number. Okay. Okay, so then p. Sorry, no p. You should correct. And now PCPI here, and this is the essentially E3, I don't remember, PI and then XI, especially XI minus 1. XI minus 1, XI minus 1 divided by H bar and minus 1. Okay. But once you see this P, once you act P on PI, this can be bring to here. You have an xi and a pi here. Now give you e to I pi xi over h bar. Okay? You agree? P squared is of pi is a pi squared. And after that you can bring it to here and you can take any product. And so therefore what you get is that the product of I equal to 1 and 1 xi I divided by a broken normalization p pi h bar e to I h bar pi x I minus x minus 1 and then minus pi squared divided by 2m plus e x I minus 1. I minus 1. Sorry. Minus 1 is divided by 2. So that's what you get. Are you with me? Is everything okay? You understand? So this guy pi squared is just pi here. And then b is the xi, so you get the b of xi minus 1. Okay? And the inner product of p and xi, here and here, will give you this term. Will give you. Now, So we take, so epsilon is going to 0 limit and goes to infinity limit. Okay? So which means that there are infinite many slits in the middle and subdivided by the very tiny infinite. Therefore, this epsilon is the sum. Epsilon can be treated as a del P. And then, so therefore, this part is just become time derivative of x. Okay? So dx dt, the same as dx dt. And this, the product over this one become the integral of dt. Therefore, what you get is that the all possible configuration, so people just have dx on dt, all possible dt, and then e to I h bar, the px dot minus e squared over 3m minus e of s, and then dt, and then e of t n equal to 0 to n. Is it okay? Now, so this x naught is a time derivative. Now, so p is a function. T x is also a function of t. Function of t. Now we perform the Gaussian integral of t squared. To be honest, I don't remember the precise form of Gaussian integral. Gaussian integral is something like this one. Dx e3 minus nx squared is equal to 3 n over n. Is it correct? I'm too stupid enough to. Let's check on it. Yeah. It's okay. Or if you do that, get more ambitious like this. Now, let's try to perform a Gaussian integral right here of p. So to do that, we form like this way. This is very standard technique in the in quantum mechanics. So this is a minus p over square root m minus square root m x naught square and plus 2m x naught square. Okay. Keep another mistake. So this is divided by 2, and this is m over 2. Okay. Minus p of x. Do you agree? Okay. Do you agree with me? Okay. So now, this part, it exactly look like this way. Gaussian integral. Yeah. Okay. Therefore, if you do that Gaussian integral for dp, what you get is that the unfortunately, I don't have a space to write that here, so let me erase here. and then it is equal to dxt e to the I of h bar 0 t dt, and then n over 2 x naught square minus b of x of dt. Okay, where x naught is equal to x naught and the x whatever t is the x and whatever, or whatever. So that's the original. And this can be understood as the d of x t e to the I over h bar s of x of t. But it's just Lagrange. So this part is just Lagrange. Okay. And here, ext means all possible configuration as I mentioned. So that's whatever configuration you can consider. Okay. That's evolution from x naught to xn. Any questions at this moment? That's particular, and I'm surprised they no one has teach this in mathematics. Or quantum mechanics too. No. Quantum mechanics too. Even quantum mechanics people do not teach you. What?
Quantum mechanics. Quantum computing.
Quantum mechanics.
The process is the next step.
Okay. Okay. So that's conceptual component. Let's do 1.1. Example. Here I have to be careful when I hear dxt is a bit cheating here. In fact, dxt you have to remark. Remark is that the dxt is in fact So this part is a measure coming from Gauss integral. So this corresponds to this solution. This square root pi over over n. This part is coming from. Because I mean you have some non-trivial factor here, right? Non-trivial factor here. You need to take in account this non-trivial factor. Okay, that's remark number one. Suppose Px of z is equal to 0. Okay. Suppose this is the case. Now for f of x is 0 t. Like this way. So then, So this is simplified. So this is the correct way. Okay. So let's check this is true. At least we can do the comparative. So this is after. So you can do the following thing. So u x of z say m plus 1 extra is equal to, we need to show that this is true. With y like this. Okay. So that's what we need to show. This is a property of this time inversion operator. Okay? Is it okay? Are you with me? So what I did is that exactly here. Okay. So at the end, so here, u of x is something like a whatever. So this is the n step and the n plus 1 step. So from here to whatever, so say, so well, this is t, and this is the x. And here you have an x here, and here you have a z here. Okay? X to z, you have whatever configuration, and here you have a y here. Here y here and a z. Okay? You understand what I mean? So from x to y is the opposite. Sorry, x and y, z. So from z to y, z to high, we have a time inversion operator. From here to here is governed by this time inversion operator. Here, and after that, you need to multiply. After that, you need to multiply u, x, y, and epsilon. Okay? And if you have a total process and integral over y, you should get this one. Is that okay? Are you with me? Okay. Nowadays, okay, so people sitting in front is listening, but anyway, nowadays there are lots of video or online video or even this video is this lecture is recorded. If you don't listen to the lecture, it's a meaningless to come to hear a lecture. So it's better to take a rest. I mean, I think it's better to. I mean, if you come to the lecture, you should focus on the lecture. Otherwise, you will lose. You will waste your time. It's okay. It's okay to skip my class. That's another way to make use of your time. But if you come to the lecture, it's better to focus on the lecture. Okay, let's check this claim satisfies this identity. But it's okay. I mean, to come to lecture is to focus on the lecture. I mean, once you look at the online, you just whatever, sitting down and then lying on the bed or whatever, and eating something, and you never focus on. But if you at least sit in the classroom, you can focus on a little bit and absorb what lecture mentioned. That's the meaning of the attending lecture. That is becomes more and more important from now on. I mean, nowadays, I mean, everything becomes online, everything, even AI can teach many things. Okay? But to come to lecture is to say face-to-face and seeing face-to-face, in-person interaction. That's most important from now on. Okay, anyway, so, okay, let's compute this one. So this one is equal to plug this one into here. Sorry, this is wrong. Still. Like this one. Like this. But now we can apply the again Gaussian integral. I mean, Gaussian integral is a bit more complicated. So sorry, I already read it. So they're a bit more complicated Gaussian integrals like this way. Exponential minus a y minus alpha e y minus beta is equal to square root of 5 n plus b. So this can be easy derived from the just usual Gaussian integral. It just shift of change of variable. Okay. And set A is equal to minus I m over 2 h bar I epsilon, and B is equal to minus I m 2 h bar and epsilon, and alpha is equal to x, beta equal to z. And you plug this one into here, and you can show that so this is another Gaussian integral. I'm going to use I. If you set this one, so what you get is that this one is equal to sorry. Like this. I just plug these numbers into here. Once you get this one. So therefore, our claim is verified. I mean, this can be, I mean, this is the induction proof of this can be treated as induction proof of this. Okay. So path integral usually cannot be performed in most of the cases, but for free field it can be. So another instance is the harmonic oscillator. Shall we do harmonic oscillator, or do you know how to do that? I mean, it's not so difficult to do the harmonic oscillator, but kind of tedious. It's tedious to derive this one. Okay, let me do sketch. Let me do a sketch derivation of the halving of harmonic oscillator. I'm not going to derive everything. It's kind of, I mean, just on the blackboard, it just takes a lot of time. But if you use mathematical and so on, it's super easy. Okay. Now we got power compounder. So I just want to use the premium version of this one. System E of x is equal to 0 and whatever t. And then what that? Then over 2 x plus squared plus m omega squared over 2 x squared. And we want to compute the past integral or okay, let me think it right like this way. What? So my notation is something like this. So minus 19. What's wrong with this?
B minus B, so you find it is
Sure. So I mean Euclidean version. So what I did is that IT is treated by tau or measured. So therefore DT is I E tau. Like this. Is there okay? Is there okay? Okay. So this is E means Euclidean version. So I use the I do the something called whatever equalization, whatever. IT is treated tau, so I think maybe I should call it this tau, and I call it T capital. Where capital T equal to beta H bar. Okay. Okay, so let me do it briefly. So let's okay. So the important thing you need to learn is that let's have x and t, whatever internal potential, this is x naught and this is x max, whatever. And the classical, it always give you shortest path. This is the classical equation only. But the quantum mechanically, you can have the whatever path you can take. So the classical is the shortest path. And because I mean, the path is, so if it is the longest, okay. So if it is Lorentz signature, the path is oscillatory. So this longer path, and if you take the fluctuation of this path, if the path is long enough, they cancel each other. The phases cancel each other because the longer path you have a more, how to say, way of like oscillating. counter, but if you shorten this path, I mean, you fluctuate a little bit, path is fluctuate a little bit. Its first derivative is 0. So therefore, this is the path which contributes most when you take h bar goes to 0. H bar goes to 0. When you take h bar goes to 0, S of E has to be minimum. The minimum configuration is the dominant contribution. So therefore, so this shortest path is the class. So let's look at the shortest path. So this Q, so this is the Euclidean action. And the Euclidean action for the solution is essentially the equation motion. It's got omega squared x is equal to t. And the initial condition is given by x prime. Capital T is given by x. If you solve this term, so x Pascal and tau is equal to x times sinh omega tau plus x times sinh omega t minus tau divided by sinh omega capital. So that's the equation motion, classical solution. The fluctuation, so x of tau can be decomposed as classical solution plus fluctuation. So this can be understood fluctuation. Plug that one into here, so SE of x is equal to SE of classical, x classical, plus m over 2 a dot square plus omega square a square. Okay. Now what we need to do is that the so this rho of x is equal to n of t e to the minus alpha h as Euclidean and the x classical. Okay. Where n of t is the either e to the minus m over 2h bar 0t and tau and either dot square plus omega square and that's what we have. Fine. So since we take the initial value like this way, so now the initial value of fluctuation is always 0. Okay, so that's what we need to evaluate. Okay. So to derive this, so what we need to do is something like this way. So we do the full decomposition of time. So now here you have a time is the imaginary time tau from 0 to capital T. Okay? And we have this condition. So therefore, what we can do is full decomposition of in terms of tau is sum over n is equal to minus infinity to infinity xn e to the I omega n tau, where omega n is called 2 pi n divided by t, or divided by the Fourier composition, if you do this, import this, you satisfy this condition. Okay? Are you with me? If you multiply, if n is of course integer, n is integer, and then plug that into Q, this maybe this is how capital T, capital T. Okay. So then this action can be understood as m capital T divided by 2 sum of m equal to minus infinity to infinity omega n squared plus omega squared then the xm squared. That's the Fourier composition. And sometimes this is called this omega n is called mathematical frequency. Okay. Sorry. So what I meant is that this action S of E, this part is equal to this part is equal to this. Okay. Okay. And then this the angle is essentially just integral over dxn. dxn. So what's going to happen is that the n of t, n of capital T, is equal to the product of the n is equal to minus infinity to infinity dxn e to e n over t. Okay, so that's and here you have Gaussian integral. Okay, xn squared and dxn. Okay, fine. And if you perform this Gaussian integral, what you get is that the function like this and product of n equal to minus infinity to infinity is pi divided by omega n squared plus omega squared and 1/2. So that's what you get. And you recall that the something like a so Euler found the following identity: h of pi z is equal to pi z, and then product n is equal to 1 to infinity 1 plus z squared and squared like this. So therefore, if you apply this mechanism, what you get is that the distance is equal to, so this one is equal to some constant sorry, I just got confused. So therefore, so if you write that n is equal to minus infinity to infinity omega n squared plus omega squared equal to omega product n equal to 1 to infinity omega n squared plus omega squared, like this way. And then if you factorize nice way, if you do the n equal to 1 to infinity omega n squared, and then what you get is that the 2 times inch beta h, so 3 times omega over t, and then times over t. So t is t. Okay. That's what you get. Is that okay? So you apply this order identity. You can just write down the EV product into inch. Inch over this. Here there's something very, very like this one is something problematic. So omega n is essentially this guy. Omega n is this guy, and you have this product from 1 to infinity. Obviously, you get infinity. Yeah. But usually, people just apply so-called zeta function regularization and so on, which I'm not going to explain to this lecture. You can treat this one as some constant. Treat it as a constant. And therefore, at the end of the day, so if you use this identity by using Euler's formula, what you get is that the N of t can be treated as the sorry, what is it? Some constant times 2 times h omega t over t. That's what you can do. And then that's what I have written in the lecture note, I think. Yes. Like this. Okay, so that's the thing we have. I think it's okay. I just got confused. Factors for the only Thomas stretch. Sorry, I got confused. Sorry, I got confused. Sorry. Huh? I don't know. My lecture notes have a extra skirt one half. But I don't know where it comes from. Oh, yeah. Don't know where it comes from. Sorry about it. I think I'll figure it out in the break. I think, okay. Anyway, so if you do that, okay, let me write that down. Sorry, what? So now for the additional function, I call it known as x prime later equal to n over t. And if you plug this classical equation to here, what you get is something like this one. So what you get is something like an exponential minus and omega. Sorry, cos e omega to x prime. Like this. So this is classical. This is e to the minus 1 over h bar s of x classical. And the n of t is, I thought this one, but my lecture notes has I'll be there about why there's this gap between my derivation on the blackboard and the lecture notes after the break. Let's take a break for 10 minutes.
这不能拆成，混组规定，溜到
Well, you can use the real expansion.
这个以后我是觉得，好的，下面这个问题，下面多了一条。其实它一打之后，我觉得非常好。说的你格，这个东西越少，够了就会像我两个好，这个 T 就是来自对这一个上来这一层，这个啊，对，有一个一直都还是应该有你们这一层还是就是过来这上面然后这边把这个上面的东西直接按个这个面还要给你那个 x 的变加，对，这个 c 还有这两个 x， 相当于就是这一层呢出来是这个，然后这个下面它出来是这个 x， 然后又下这个这样那个就是能后面这一层，就是这一层再算一层，这个下一层。对，这个它，对，都在一片，对，这都在一个场，这个是这个下面的，然后虽然这个像现在是这个不是这个，对，这样这个会出现特点。就是为了什么？因为就是我是从这个对于这个我拉回对于这个数这个当时这个对就像 S 也是对 它的这个定义是错的，这项是已有的税，这项已经有的税，就这个说的是哦，对，说的是后面这个，扫边的这个说的这个和这个最少数就是这个作用的 PI 上是都在的，然后剩下这样。现在我是对这个东西就是你不能把单独行业成就是的，也是可以不可以，那不能拍，不能拍，因为底下你们这套可以控制，就是相当于就是他把时间替换掉，对，他把时间替换掉，其实我接受这个，我也我接受他这个节奏，我放，这样放。对。啊，因为我们这个肉，它这个肉。它这个肉的这个形式和这个时间演化断层的形式很像，它这个这个是里和这个后面这个时间演化断层是长这样的，这个单独就是任何一个本身的数作用在这个，就这东西作用它到底是怎么样？它的下面这个对，这个。这个东西我是拿来说，这个是算这个相当于是你这个肉就是它只是和前面这个。它是什么作用的演化？就是那个规则它是一样的，所以是不能拿出来说这个应该是一个完全可以对加对，他认为这个就是认为这个IT 的非它是真发性，这个是对，就在你看这个T 的方式写的是大家到小 T 的体内的话。对，这个那个也算是干哦，对，然后小店那个上面对，就相当于是在到这个一趴的，现在这边没有就然后呢，这个考虑也算是将来讲解它的在抽取增长的是把这样一个像这条是就是在这个在未来要让它的时间是可以是关于一下这个演化，它说是上面有一个 H 看。就是有一个下面，然后再观察一下这个后，就反正PM 的对类比是把这个说把这个列比这是一的，其实也能相当于我们新构造里面超太多。可以对，只是位置的一个P 是公的呀，这一个对啊，一可以到它的这一段时间内进行 P 跟 S 对应，哦对 P 跟 S 还可以，对的，这可以非法或者 S 和上面的这个 ，So you can't just like this M gives 对比对，主要是非常把类比的一个时间，然后所以说类比这个约定，对他那个 T 是我们一个前面是得到了，这它都是个变，这条可以写我们可以写它这个逆这个变换在这个位置的 X 下的，就是说它这个带来的方式。它其实应该是负的，还给点一点房价，那不减价的点，那咱们整个报都给内部之前应该是X 把给分成两项，对，像这个 这个我代表这边是哪边的那个 IT 和那个 IT 的那个主要是要把这个一它这样方面，这个突然来，刚才学的时候，对，我们应该是这么说。没音去年后之后最近几段，最后来一是加一是投资的，就这儿这个这个加了种包括加长肉就变成这样别这个所以的话，按这个应该是
我也有，但是这个
就是今天哦，就今年解放好，那是这我有接受。我
不太知道是怎么，但是变成肉了，之前不是丢吗？
前面的都是一个，就是那个之前的质量处理一下，那么
之前写的这个丢的，
那个都还没有，这个社会。
你看它这个丢的，后来变成肉了。
这个球还不是这个 P 跟那个 P 方跟它表示一个，它的对义词跟 P 方跟 B 应该都不是对义，因为毕竟 D 是一个比较奇怪的函数。这个说来记住，那就把它什么搞？你甚至都不能是啊，不是开始那边的一个叫 R 乘这个，这个东西反正是
这个东西，
对。这个很搞笑，
这个东西，
然后也可以，要么就是本身是刻意准备，要么就是刻意本身思维，那就这样。确实是，
前面讲的丢的。
你的你有什么新的结论吗？我是上班时候，对，确实我看到那个技术啊。
这个式子都跟我说，
我感觉是个对，这个其实，我也没来，
应该是到后来他算，
就算他们对，是不是还是他是这个意思，但是勉强
不对，一的话，他加法的这个还能可以拆吧？不是，你这拆成两个东西合起来就是瓜。
不，这个对，基本上对，以至于反正就
拆成两个东西乘起来，
这玩意儿到这里这个，这个就是这。
让他一，
但是我习惯。这玩意儿，这个加法跟交法那是完全没有影响。
对，没问题。加法里面是有加法的，这个确实是。
加法铁没问题。
非常就是这个到这个就是你把那个 n 的零的乘法，应该平方
无法理解，但是会不会这个东西做一个对称化？
都刷写出来的。
都对称化。
这里面有一个，
就是这两个玩意儿，加上再造一下，然后名字一拼过来。
不是，就是如果你说那个公式的话，它要求的是必须它的对义词就是一方跟 B，
一方跟 B
的对义词要跟 B 对义，一方是对义，对吧？要有一个公式，这个东西都不一定成立啊。这个 B 是什么样的？
这个东西不一样，
this has to be true. Only if it's a good
I mean, here you have the zero and 1 and 2. How can you have an all possible ending?
然后他又维持了这种给
all possible state. How can you all possible ending?
所以它最后算出来这玩意儿是怎么个处理？最后它这边那个东西啊，那贝塔178是啥？确实挨刀的，一般是胶原，对，然后贝塔是 KT， 放别它就简单了，那确实是 we also have X here。应该是这个。他写这个题的这个贝塔178。它虚实间是什么？对，好像是。对，虚实间就是对，解的是谁的比那个微分？对，这里面没有温度答案。这里好像是也没有这个 T 是有，T 里面是有温度。对呀，对。啊。对啊，非常有帮助。对呀，这个大气层贝塔178是啥意思？都是最大值的。对啊，为什么从0知道10？计算这个率是多少算出最大的数？就道理简单，反正没看懂。
我也
我还是觉得这个贝塔就是这个原因。T 等于超就是纯一个数学上的组配，但是这个 T 等于贝塔178。那个是基的主体方的。对呀，那为什么这个中间取贝塔178？他讲其他就说了，这个接最大就是用一个算子所以我现在就非常好奇，讲会是用一个一点，因为我会看这个东西和我找一种。哎，等我一种来。对，我没有理解为什么不写这样，就这个房子在市。
I mean, it's only I can just physical schematic of it.
This one is just the definition of it. The definition of yeah. It's just the definition of yeah. I understand why critique 这个在一起吧。Wherever is the but beta theory is one of everything.
那以这个表示啥？在边上。I want to take my player H 卡。那我现在就
啊。
这个东西全都写出来了，然后这个这个我上去你把第一个数列上去以后，第二个第一个它肯定是不一样的。这就是不可能的事。
I will spend second half. I think your problem, what you point out is yes, yeah, I agree.
是问题了。
我的人运气
然后然后这是突然到这个位置。
哦，原来是这样。
我无法理解。一个问题啊，还是那个是它是呢。
这个配合是说是所的是配合，我们有没有说是这样子？我说。
Yeah, the one way to answer this one is the following. That's why I wrote this one is the xi minus 1. Xi minus 1. This one is x. And this is xi, right? And I put the pn, right? pi, right? Then you hear pi squared and then the xi squared. You don't need to worry about commutation relation. This is the xi derivative, right? Here is the xi minus 1. That's one way to avoid commutation. Like a commutation relation.
还是先把拆出来抽出来。拆出来抽是不是 x？
I still don't have an answer to why I have a Yeah, I think I missed something. I think it's better not to waste your time. Okay. Okay. I think it's okay. Let me continue. So many things people ask. Let's do one by one. Okay. In my lecture notes, N of T is written on M omega divided by 2 pi h bar h T omega after T of the 1/2. And addition function is whatever E h T omega over T. So this is compatible what I did here. Yeah, this is compatible. After some authorship, which is not important. That's what I thought. But my lecture was somehow we have some somewhat weird 1/2 factor is on over 2, and then some factor here. I kind of don't know why. I sorry. There are lots of questions during the break. I didn't have a time to figure it out. Maybe next lecture. So this gap is the. I will answer next lecture. Sorry about it. Where's the gap? It's the gap between them, which I don't know. Does anybody know answer? How do you fill the gap? Okay, nobody knows. Okay, then I will answer this gap next lecture. At this moment, I don't have answer on top of my head. The second is that the y I wrote different rho xx prime value instead of u xx prime whatever. The question. I think this is a normalization issue. So when I give a path, okay, before the gap is related to what I'm going to say from now. So here instead of the usual path integral is something like x of p and e to the I over h s of x. So that's that local solution. And this one I call it the u, x minus prime, whatever, t, t, x0 and x prime, x capital T, whatever. So that's the time evolution of adaptation. And then in the counting oscillator, I use a visualization such as the x0 and x prime e to the minus 1 over h bar s of e x is in Ukrainian. And I wrote this as rho x and x prime and then whereby there h bar is equal. So the reason why I don't like this one is to connect that symmetry and give a half-integral interpretation of the half-integral interpretation of the symmetry. Secretly, I secretly introduced the before I explain. That's why I use rho. Before I use rho. So rho, if symmetry is by e to the minus beta h hat, then e canonical function. On the other hand, operator u is given by e to the minus I h hat t over cap h bar. According to my notation, this is the okay. And so that's like it. How do you relate between them? So to do that, we treated this is the imaginary time and small t, and they are related by tau and then by h d divided by up to h bar, up to h bar. Therefore, this tau can be treated as Euclidean time. And then the density matrix is the evolution of the imaginary time. Imaginary can be treated as imaginary time. And in particular, if you consider rho of x time of failure, what you get is the essentially x and e to the e. Minus beta tau. Oh, sorry. That's what we have. Therefore, we have the whatever. So this is x. This is the imaginary time. And if you have x prime here, and when tau equals to 0, and tau equals to failure, scaled by h bar, and you have the x variable. And this can be understood as the whatever. All possible paths you just treated from x prime to x in the imaginary Euclidean time. So density matrix can be treated as the path integral in the Euclidean time. However, that's the case. Moreover, what's important is that when you consider the partition function of the system, the partition function of the system is the, I'm going to so partition function of the system is that the Z is equal to trace of rho hat. Rho hat. The important thing is actually yeah. Unfortunately, I'm doing something. That's why I made a mistake. This is U. U means abnormalized. This normalized one is tau over h hat divided by z. That's the case. If I choose rho hat is U, and this is U. Then this is U. In fact, it has to be U. So U means abnormalized. That's why I think I made a mistake in color. In this gap is related to this. So let's first consider abnormalized density matrix. It's just the overall factor by partition function. So this means that the trace means that the this is the minus infinity x naught e to the beta h hat x naught. You start with the this is time, imaginary time, and then tau equals to 0, and tau is equal to beta times h bar. And then trace means that you just integrate over all possible function over dx bar. Yeah, okay? Is that okay? Trace means that so here is x naught here, has to be equal to this x naught here, and you integrate over all possible positions here. So this means that you just identify this position and this position, okay, and then you integrate over. So this means that space-time is just if you identify and the left side and right hand side, what you get is cylinder, where circumference is given by beta and sum. So therefore, partition function trace means that you just integrate over how to say all possible position in here and here, identify and integrate over. So this means that this partition function is in fact the partition function of a cylinder. And this is Euclidean time. So this part is Euclidean time. Right? Which is circumference. Circumference, right? It's better than this one. So that's the particular meaning of the partition function of statistical mechanics. And the reason why I didn't get the correct entity is that if you just appropriate normalize, so this is I think normalized one. D is the integral of unnormalized. So the difference is that so integral over dx rho x prime of beta has to be equal to 1. And this n of t is chosen in such a way that this condition is satisfied. So if you just do that, identify x and x prime, and do the Gaussian integral, you will get exactly n of t. It should be so this part, and do the Gaussian integral. So what we need to do is that you just identify x and the x here, and then do the Gaussian integral dx from minus infinity. Then this will become the whole integral should become n of t inverse. That's what I need to do the computation, and that will cancel and they give you 1. So that is expression of rho. That is a whole. Normalized. This is normalized. But the partition function I computed before the break is in fact unnormalized. That's the difference between these two. Alright, so that's the key. Alright. So that's what I do get with that. Any other question? Okay. So I will explain some other notion of reduced density matrix. Reduced density matrix. So reduce the matrix. So raw part is one part of me. And then again okay. But reduce the matrix as follows. So row of n x1 equal to xn and then x1 prime xn prime is just expectation value of this ratio operator. Yeah, so the expectation value of this okay. Where the here what you get is sum over mu and so expression of operator is trace of raw path and then operator or half, right? And plug that into here and then just sum over all possible mu. So this means that the difference is given by W mu. This is just normalization factor. Yeah, normalization factor. And then factorial I S so n plus 1 5 mu and star of mu plus prime equal to prime plus 1 like this. So let's digest one by one. Let's digest one by one. Sorry, I don't remember the definition of. Sorry, I'm confused. How do you deposit psi of mu? Let me think. So my definition is the psi factor of x1 is of empty is x1. Is it that correct? Definition I already forgot. Is it correct? Second quantization we know, right? How do you find the x1 state? Let me recall. just a moment. Yeah, so that's my definition. So basket is there. And then what I did is that so here for the psi new and then x1 total xn let me recall, sorry, is equal to psi mu of star and then x1 total x and mu. Sorry, I'm trying to recall my notation. This is no star. And then the opposite x1 total xn is equal to psi mu star. It's the x1 total xn. Okay, so that's the notation. And then to compute this quantity, what we need to do is that the phrase of rho hat and the psi dagger, and psi. That's what I need to do. Psi is over there. And then, so therefore, this means that the let me consider. So x1 total xn of psi mu W times I think how should I do it? Sorry. Oh, now I'm done. Okay. Let me write that. I already forgot. You must have already forgot. I should do one more time. Okay. Okay. So now let's do the point. So dx1 together total dx and nu together x1 together total x2 and nu together. And I think I should start backward. X1 total start backward and more than and I nu and W nu. And then here I should put phi nu. Hopefully I will get that correct. Okay. Now how notational mistake I made. There is some notation mistake. X1 here total and here sorry. Psi x1, so this is prime. And like this. Okay. Okay. So this is we have roll. That's what we have. And here, if you just apply this into here, what you get is the delta function x1 here minus x1 prime function here. Yeah, that's not good. What I'm doing. Sorry, I got confused. sorry. Sorry, I'm working here. Sorry, no. No, sorry. Okay, sorry. Let me do it again. Sorry. Tiny. Okay, this is okay. Now for this is equal to. Sorry. And then this is pi nu x1 x n. Okay, that's fine. Now if you apply sine of x1 x of pi nu, then this will give you as follows. So this will give you psi of x. Yes, sorry. Now prime or tilde, sorry, tilde. Psi x1 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 tilde x and mu tilde and phi of mu x1 tilde x and mu tilde. And if you do that, apply on this one, this means that this will give that you have a delta function equal to here and x function. Okay? So therefore, you perform the x1 integral, what you get is the appropriate normalization, my normalization, something like that. And it is like this way, and then d x2 to tilde, x and mu tilde, and then x2 tilde, x and mu tilde, then phi of mu, this is x1, x2 tilde, so x and mu tilde. That's what I said. And the same thing you can do that. Sorry, now it should be okay. If you apply psi x here, then you have a psi x2 here, x of here, that what you get x. You kill them as x2, and then you just get rid of this one, and you start with x3 tilde, and then you just get x3 tilde. Okay, and instead you have a new manifold, and so on. Okay, is that okay? So, you understand? So therefore, at the end of the day, so what you get is therefore, whatever. There's an ordering issue here, but it doesn't matter. And then what we get is that um, I need, and then take one, and here, and new here. And that's fine. Okay. So this is one side. The other side is the exactly come from the opposite side. So what we need to do, sorry about it, phi of new and the psi dagger of x1 prime, psi x and prime, you will get something like the very similar term. So this part is the same, integral same, but here you have x tilde and plus 1, x and tilde and phi new star, and x from prime, over x and prime, and the directly the same. Like this. Okay. Then, the thematic role is essentially of n. Is essentially n. What you get is that the is time of mu, and then psi mu, and then psi dagger, and psi mu, and omega mu. Okay, omega mu. Therefore, if you combine them together, what you get is sorry about this part. In particular, if you apply this law 2, for row 2, x1, x2, x1, x2, and this is the psi dagger of x1, psi dagger of x2, and psi x2, psi x1. Yeah, I think the internet computer. Yeah, this should be n2 n2 sorry about it. And this is equal to sum of nu, w nu, and the nu, and nu minus 1, and then ex3, t, x, and mu, and then psi mu of x3. Okay. And then from now on, we try to derive different rho of 2 in some particular system, some Fermi, two particle correlation function in some system. And so this is called pair distribution function. So that's what we are going to compute from now. Okay. Any question at this moment? So, sorry about this derivation. I was stumbled such a technical derivation. Sorry about it. Any question at this moment? So to derive that, we need to use so-called block the Dominic theorem. So this is another way of saying Wick's theorem, actually. Okay. So we are going to compute this quantity from now. So the goal is compute rho of 2 x1 x2 x1 x2 in some simple system. Free, boson, or fermion. Periodic bosonic system. So this is another way to say that the compute so-called, this is called did I write? This is called something called the correlation. Two particle. I think we did I write the two particle? No, it's okay. The name is okay. Okay. So that's what I'm going to do. So physically, what we are doing is the problem. So here you have a system, very big system. You have a state nu. State nu has a number of particles and nu. The particle display whatever. There are many particles, but we fix the particle of the some position x1 and x2. You fix the particle x1, x2 here has the particular position x1 and x2. But however, you just integrate over all possible other configurations, whatever x3, x4, and you just integrate over all possible the particle configuration for apart from x1 and x3. That's what I'm doing. So that's what I'm going to do. So that you have to integrate over everything. So that's the meaning of reduced density matrix. Reduced density matrix is that you specify a particular subsystem as fixed position is operator, but you integrate over all the other all the others. So to compute this quantity, we apply so-called statistical mechanics is called, I didn't know that actually, log. community. So this is statistical mechanics community, mathematics community. I didn't know that. And QFT community, it's called, this is QFT community called quick contraction. It's the same thing. They just have interest in different motivation. That's what we want to do from now. Okay. So to do that, we just move on to the so and then we just consider grand chemical sample. Okay, sample which is given as follows. So H, free, non-interactive. I shouldn't say free, non-interactive. Non-interactive. So H current hat is H0 hat minus mu and hat, and which is given by Ex plus x e square over 2n plus u of r minus mu times psi of x. And if you do the Fourier transformation to the momentum space, what you get is sum of q, epsilon q minus mu, and this is q dagger. Okay, that's what you get from momentum space. Okay, and then rho hat implies sum over u, and then sin u, and then e to the minus layer, epsilon u minus mu, and then u, and then and 1 over c. 1 over c. So that's what you get. So to the space here, and we remember that the log of the ground potential is the beta times log omega. Log v. And minus sign. Minus sign. I think I'm doing something to this inverse. Yes, inverse. Okay. So therefore, if you plug that into here, this can be understood as sum of nu, phi of nu, e to the beta omega minus beta Kali H hat d. So as I mentioned, so this is the square H, this is Kali H. Square H just the Hamiltonian of the system of a particle. Kali H just shifted by mu to the numbering operator. Okay. Fine. And then fine. Oh, sorry, no. Thanks. Therefore, so essentially, what I meant is just a simple thing. It's just that E to the beta omega minus beta H hat. Curly H. So this is the density method. Normalized. And then Heisenberg picture. If you go to Heisenberg picture, of the operator, so the C hat of Q of beta is given by e to the beta highly H C hat, and then C hat of Q e to the minus beta H highly H hat. So this is the how you define the time evolution of grand canonical ensemble. So everything instead of in grand canonical ensemble, instead of this square H, you have to use curly H hat to consider this imaginary time evolution. That's what I mean. Okay. And then so the statement, I don't have a time to the statement of the log theorem is as follows. If you consider correlation function, of course the correlation function is just that always assuming is trace of all paths and all paths. So this is a correlation function. You have expectation line, whatever you call it. So even number of distance is the trace of e to the beta omega of minus h equals and c1 and p to n is given by contraction, all possible concrete of contraction p and ct1 equals 2. That's why if in the odd number n minus 1 we have n. And the p is that all possible permutation. P is permutation. Let's see what you mean. So you can just consider graphical. So then, I'm going to derive this theorem in the next lecture. You have an operator 1 or C1. That's I don't know why I use C1, C or instead of O, but it's the same. C2, C3, and C4. Okay. So if you consider the following thing, to compute this whatever correlation function or like this whatever pair distribution, whatever. So you just have a this one, or this one, or this one, or this one. So this is the C1, C3, C2. Okay. So this is C1, C2, C3, C4. And this is C1, C4, C4, and C2, C3. That's what I do. And to sum them up, it should be plus sign, and here you just opposite. So if it is the fermion, it has to be minus sign. And this should be plus sign. That's how it is. This expectation line. It's a very simple graphical interpretation. The derivation of this theorem I will explain next lecture. Let's start. Okay, if you have a question, just come to me. I will happy to answer.